Picture the most improbable event you can imagine. Something you would think is virtually impossible. Now think about how long you should wait for such a rare scenario to repeat. What about a large set of extremely unlikely events? Imagine the unfathomable length of time required for those events to repeat themselves. A timescale so vast that it dwarfs not only the age of the universe, but also its entire history, from the Big Bang to its ultimate end. And finally, imagine the craziest of all, the universe in its entirety repeating itself, linked to the biggest number ever calculated, a figure so enormous that defies comprehension. All of these intriguing thoughts point to a single overarching concept: Poincare recurrence. Poincare recurrence is a concept derived from statistical mechanics. It says that under certain conditions, a physical system will, after an immensely long but finite time, return to a state very close to its initial or maybe even the same exact state. This recurrence applies to the systems that are isolated, meaning they are closed and don't interact with their environment, so the energy and mass within the system are conserved. The concept doesn't apply to any system with an infinite number of particles or infinite volume. The time it takes for this recurrence to happen can be extremely long, depending on the complexity of the system and the initial conditions. Imagine gas molecules being released in a specific corner of a closed box. The box is sealed, so no energy or matter can enter or leave. It's also totally isolated from its environment, so no external energy or matter could influence the gas inside. This is a highly ordered state with low entropy, as all the molecules are clustered together rather than spread out randomly across the box. Entropy is the inherent tendency of energy to spread out. It measures the likelihood of a system being in a specific configuration. An orderly system has low entropy. A disordered system has high entropy. A system is more likely to evolve towards a state of disorder. Immediately after release, gas molecules begin moving around randomly inside the box and spread out more over time, simply because that's the most likely outcome. So this is a perfect example of an isolated system with a finite amount of possible positions and velocities of all the gas molecules. As time passes, the gas molecules will move around due to their thermal energy, colliding with each other and the walls of the box. Gradually, the molecules will spread out to fill the entire box more evenly, which aligns with how any system evolves entropically over time. The distribution of molecules will become more uniform until entropy reaches its maximum, meaning the gas molecules are almost evenly distributed throughout the box. Now, if you wait long enough, statistically after a very long time, there's a non-zero chance that the gas molecules go through a spontaneous entropy decrease, return to a state very close to the initial one, where they are once again concentrated in that same exact corner of the box. Even though the system eventually returns to a low entropy state, this does not violate the entropic law that insists on systems naturally moving towards a state of greater disorder or more entropy. The reason it doesn't count as a violation is because the time spent in high entropy states is overwhelmingly longer than the time spent in the low entropy state. So based on Poincare recurrence, an isolated system like a sealed box of gas will, after an extremely long time, spontaneously return to a state very close to its initial conditions. For a typical box of gas, the recurrence time might be far longer than the current age of the universe, which is more than 13 billion years, making it an event of theoretical interest rather than something observable. If we imagine the universe as a closed system, the idea of the Big Bang being a low entropy state could be seen as somewhat analogous to the Poincare recurrence in a box of gas. If the universe is a closed system, meaning it contains all the energy and matter that exists with no exchange with anything outside, then the Poincare recurrence theorem could in theory apply. The Big Bang represents an extremely low entropy state. All the matter and energy of the universe were concentrated in a tiny, incredibly hot and dense region. This is somewhat analogous to all the gas molecules in the box being crammed into a corner. After the Big Bang, the universe expanded, and entropy increased as matter spread out, galaxies formed, and the universe cooled down. This is similar to the gas in the box spreading out to fill the entire space. Now, is it possible that all the matter in the universe returned to a state very similar to the Big Bang? A low entropy, highly ordered state, just like the gas molecules in the box randomly converging back into one corner after spreading out? The same Poincare recurrence could be applied to the universe as a whole. The number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. Every single atom could be arbitrarily returned to a state similar to the initial state of the Big Bang after an enormous but finite amount of time called Poincare recurrence time. As a result, a new Big Bang could emerge. In physics, within a closed system, energy and sometimes matter are conserved. This means that the total amount of energy and matter stays the same over time, can't be created or destroyed, and can be only transformed from one form to another. A closed system doesn't exchange energy or matter with its environment, whereas an open system allows both energy and matter to flow across the boundaries. In cosmology, the term closed universe usually refers to the geometry of the universe with positive curvature, often visualized and simplified as being the surface of a sphere. If you travel far enough in a straight line in such a universe, you will eventually return to your starting point. The other alternatives are an open universe with negative curvature, like a saddle, or a flat universe with zero curvature. If the universe were geometrically closed like a sphere, it would contain a finite amount of space at any moment and potentially a finite amount of energy and matter. Our universe has a cosmic horizon, a boundary beyond which we cannot see or interact, like the event horizon of a black hole beyond which nothing can escape. The cosmic horizon is a boundary that extends beyond our observational reach due to the accelerating expansion of the universe, which at some point would cause distant galaxies to recede faster than the speed of light relative to us. Even if the universe is finite, the expansion prevents galaxies from coming back together. The region within our cosmic horizon is called observable universe. The cosmic horizon doesn't imply that the universe is losing energy. Objectively, things moving beyond the cosmic horizon are not lost from the universe. They're just beyond our ability to observe, receive information from, or interact with in any way. The expansion doesn't cause our local universe to lose energy in the sense that energy is leaving the universe. The energy that goes beyond the observable universe simply becomes inaccessible and unobservable. This suggests that the universe within our cosmic horizon could be considered a finite and isolated system, but it's not a closed one. So unlike a classical closed system like a box of gas, where energy and matter remain constant, The observable universe is subject to the dynamic effects of cosmic expansion. This undermines the strict application of Poincare recurrence, as the system is not truly closed. Dark energy expands the universe, causing galaxies and other intergalactic matter to move beyond our horizon, resulting in a continuous decrease in the energy density of matter. So the energy within our horizon is not conserved in the classical sense. The space between particles is growing, and in many cases, it's growing faster than the speed of light. Particles move beyond each other's cosmic horizons and can't return to a previous state or configuration. This expansion is not just objects moving apart, but space itself is stretching. So in a cosmological context, especially with a dynamic space-time like in our universe, energy conservation is not as straightforward. The expanding universe complicates the definition of a global conserved energy. But even in an expanding universe, Poincare recurrence might still be theoretically possible. It's been argued that the observable universe is kind of closed system in a thermodynamic sense, because it behaves like a finite system with a finite number of states. Thermodynamics refers to how energy moves and changes form, especially as heat in physical systems. If we treat the observable universe as a finite system in terms of the number of particles and possible states, it would be theoretically possible for the system to eventually return to the previous state. The expansion of the universe is linked to entropy increase. The entropy of an isolated system tends to go higher over time. Just like how gas molecules within an isolated box tend to move randomly and spread out evenly throughout the box, as the universe enters the degenerate era, an era when stars, planets, and galaxies gradually turn into dead remnants, the accelerating expansion causes particles to spread increasingly apart throughout the universe. As this process continues, the universe's overall entropy goes up, driving it towards a state of maximum entropy where everything becomes uniformly dispersed. All the energy is evenly distributed and no more work can be done. This is the heat death of the universe. The quasi-isolated universe with a finite horizon and finite energy content, in its ever-expanding state, dominated by dark energy, and in its maximum entropy mode, could theoretically go through Poincare recurrence. The idea is not that the observable universe will return to an exact previous state with all the same particles, but it could return to a state that is statistically similar to a previous one. As the observable universe loses particles, it becomes a new and smaller finite system with its own finite set of possible states. Within this new system, the remaining particles could theoretically arrange themselves in a way that mimics a previous state of the universe, but it wouldn't be identical to any past state of the original larger system. Each recurrence would restart the universe, but each time with slightly different initial conditions, resulting in a new version of the previous universe. If the universe eventually reaches a stable and constant expansion rate, Poincare recurrence could become more plausible. However, there is no evidence to suggest that dark energy's current trajectory will change in the foreseeable future. Also, some cosmological theories, like the cyclic universe model, suggest that the universe could go through a series of expansions or Big Bangs and contractions or big crunches, which could be somewhat related to the idea of Poincare recurrence. For the universe to contract, dark energy would need to either reverse its effects or dissipate over time, which is not supported by current observations. Poincare recurrence time for a hypothetical box containing a black hole with a mass equal to the observable universe is 10 to the power of 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 2.08 in Planck units. Planck time is the smallest meaningful unit of time in physics, approximately 5 times 10 to the power of negative 44 seconds. The number is so astronomically large that from our perspective it's effectively the same regardless of the time units used, whether Planck times, years, or millennia. Before the Big Bang, the repulsive force of cosmic inflation caused the exponential expansion of our bubble universe in a fraction of a second. Our observable universe as a subsection of this giant bubble is limited by the speed of light and the age of the universe, which is around 13.8 billion years. The radius of the observable universe is about 46 billion light years, or about 14,000 megaparsecs. 1 megaparsec is around 3.2 million light years. Once cosmic inflation starts, it ends in some regions but continues in others, leading to the creation of bubble universes within a larger multiverse. Each bubble universe could have different physical properties, and inflation continues indefinitely in other regions. The recurrence time for a typical bubble universe produced by chaotic inflation is 10 to the power of 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 1.1 years, an extraordinarily large number. The calculation highlights the vastness of timescales involved in cosmology, particularly in models of the universe that involve inflation and eternal inflation. The size of our entire bubble universe is not directly measurable because we can only observe up to the cosmic horizon. Based on theoretical models of cosmic inflation, quantum mechanics, and general relativity, the estimated size of our entire bubble universe is 10 to the power of 10 to the power of 10 to the power of 122 megaparsecs. This is not a definitive estimate, but rather a theoretical value. The distribution of matter and energy in the universe and the dark energy are parameters that help constrain models that estimate the size of the entire universe. Given this estimation of the universe's size, it's been calculated that the Poincare recurrence time for a hypothetical box containing a black hole with mass equal the mass of our entire bubble universe is 10 to the power of 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 122 Planck times, millennia, or any other unit of time. A truly incomprehensible amount of time that goes beyond any ordinary measure. The strangeness of these extreme scenarios isn't just in their improbability, but also in their counterintuitive nature. Observing a galaxy or an entire universe transitioning from high to low entropy or moving from disorder to order would be like watching events unfold in reverse. Imagine watching a movie in reverse, or some grains of sand on a beach being blown by the wind and spontaneously forming a specific set of numbers, or clouds in the sky gradually arranging themselves into a specific sing lyric. This would be an extremely rare event. Now scale that improbability up to the scale of the entire universe. There are 10 to the power of 80, 1 followed by 80 zeros atoms in the observable universe. Trillions and trillions of particles would need to march towards a specific direction over billions of years to create the very low entropy state and initial conditions of a new Big Bang. The rarity of such cosmic events is mind-boggling, and yet their probability is not zero. Observations confirm that our universe is smoothly and uniformly expanding, growing larger at a steady and predictable pace. Dark energy drives this expansion indefinitely and maintains its effect over time. Eventually, the only thing that will remain in our observable universe is the merged galaxy Milkomeda, the result of the Milky Way and Andromeda galaxies getting gradually closer due to their gravitational bound, merging and ending up in a larger unified galaxy. Interactions with anything beyond the cosmic horizon, which in this case means beyond Milkomeda, would be impossible. Our future galaxy will essentially become isolated from the rest of the bubble universe. If dark energy doesn't increase in strength, Milkomeda won't be torn apart and will remain as the only galactic structure within our cosmic horizon. Any alien civilization evolving within the galaxy during this era of the universe will look around and see nothing but emptiness beyond Milkomeda. They'll be surrounded by blackness, a total emptiness that used to be filled with vibrant and diverse cosmic landscape. They would look into the vastness of empty space beyond the galaxy and see nothing but an overwhelming void extending into infinite darkness. At this point, the galactic structure can be considered a self-contained and closed system where energy and particles are conserved. Over an extremely long period, as entropy increases and Milkomeda degenerates, the observable universe could reach a state of maximum entropy. At this point, theoretically, Poincare recurrence could occur, where the remnants of Milkomeda might eventually return to an earlier similar state. However, as Milkomeda degenerates, its particles may gradually become gravitationally disconnected and exit the horizon. This means that the galaxy would lose some of its matter, making it impossible for it to get close to its previous state of existence. So in this recurring case, something similar to prior Milky Way and Andromeda states might originate, when they were younger, with different star formations, planets, black holes, gas distributions, and so on. Even for systems much simpler than an entire universe, in this case a galaxy, the number of possible configurations is still unbelievably large, considering the complexity of the whole galactic system with its trillions of stars and other celestial bodies. So the Poincare recurrence time would be so vast that even in this case, any realistic scenario becomes more theoretical than practical. Many activities within the galaxy, especially the more extreme ones like black hole formations, would make any exact recurrence of an earlier state increasingly unlikely. During each Poincare recurrence, in the case of happening, some particles would exit the observable universe and cease to have any causal connection to the remaining contents of the universe. In the final stages, every particle will be isolated, with no other particles within its observable horizon. The universe would be an extremely cold and empty space, with all particles separated from each other by vast, unbridgeable distances. This process would ultimately lead to a state where all structure is lost, and the universe becomes an empty void of isolated particles, each drifting away from the rest. At this point, the concept of Poincare recurrence loses its relevance, because there would be no way for the universe to reconfigure itself into any previous state. Calculations for Poincare recurrence times serve as theoretical exercises, pushing the limits of our mathematical and conceptual understanding. These figures are the longest finite times ever calculated by any physicist. These calculations emphasize the extreme improbability of such events happening in any realistic sense. Even for a typical closed box of gas molecules, the Poincare recurrence time is far beyond the lifespan of any experiment with current technology or even the age of the universe. Because of the extreme timescales involved, observing a Poincare recurrence remains unfeasible. In a universe that continues to expand indefinitely, particularly under models of eternal inflation, the idea of a Poincare recurrence becomes more speculative. While the theorem is mathematically sound, the recurrence times are typically so long that the concept is more of theoretical interest than practical concern. Given the insane timescales involved, no observer today or in the future could witness a Poincare recurrence. The universe is not only expanding, but it's also undergoing changes that may make observing such a recurrence practically impossible. A hypothetical godlike observer witnessing a cosmic Poincare recurrence from an external vantage point would see the universe's states and their recurrence patterns without being part of the universe's temporal progression. For some highly advanced observers within the universe towards the end times, the situation would be different. Those observers will be part of the recurrence process and will be thermalized before being able to measure anything, meaning they would be integrated into the system's state and unable to view the recurrence from an external perspective. Observer of any kind is a low entropy entity with some organized structure. For a recurrence to be meaningful, the universe needs to reach a state of maximum entropy where disorder is at its peak. At any point, any observer would be part of that high entropy state. So it's impossible for observers as structured and organized entities to observe such a process from within a high entropy state. But what if it were possible for new forms of conscious entities to emerge from this ultimate disorder? In fact, the very presence of maximum disorder might be a prerequisite for such entities to pop into existence. These entities could come into being not despite the chaos, but because of it, capable of observing a version of the cosmos we could never get a chance to see. A way of the universe resembling itself into patterns once again. Stay tuned.